Hi, welcome to the next lecture in this course on Haskell. In this lecture, we will look at a very important concept, that of lists. So, in most programming languages, there are ways of talking about a collection of values. So far, we have seen a few simple types: int, integer, char, bool, etc., float, double. We just saw them being used. Okay, but now, and we also saw a few small examples of a function returning two integers at the same time, div mod. It returned it as a pair. So you can for now think of it as of type integer arrow, int arrow, integer comma integer. Right? But suppose I want to return multiple values, or suppose I want to consider a collection of marks for various students, let us say, you need a way of representing these values, and that is done by lists. Yeah. So lists are used to describe a collection of values. It is very similar to array in other languages, in the sense that arrays are the basic means of representing collections of values in other languages. In Haskell, it is lists. It is not similar to array in the sense that certain operations are costly. As compared to arrays. We will see what they are later. Okay. So here is an example of a list. 1, 2, 3, 1 is a list of integers, is a list of values of type int. True, false, true is a list of values of type bool. So when we talked about div mod returned div mod of n10 was some d comma m. But you could also think of, in this case, the pair, both values of the pair are of the same type. This is int and that is int, or both are integers. But you could also think of some other functions which return two different things. Maybe you have a function that returns a string and its length, some function on some input. Maybe its input is int and it outputs a string comma int. This is possible. So the point is that in pairs or triples or in general tuples, the different components can be of different type. But in a list, all elements must be of the same type. There is a difference though. If I talk about a pair, it can only store two elements. If I talk about a triple, I can only represent three elements. But a list can represent any number of elements. Yeah. So list of bool, which will be represented as this type, can represent Boolean lists of any length whatsoever, but all elements should be Boolean. So let's see what are all the elements of type Boolean. False, of type list of Boolean, the list containing false, the list containing true, the list containing false true, the list containing false false first, the list containing false true, and then on to 3 element lists and so on. But all these are elements of type list of bool. Okay, so there is no restriction on the length of the list, no restriction on length. But restriction on the types. All elements must be of the same type. It could be a list of char or a list of bool or a list of int, but all elements must be of the same type. You cannot write, for instance, this 1, 2 true, because these two are numeric values and that's a boolean. This is a numeric value, this is of type char. You cannot mix and match types inside a list. Okay. So now if you have type T, then you have a new type which is list of elements of type T. So we have already seen a few types, right? So int, integer, char, bool, string, float, double, etc. Corresponding to each, there is a list type. There is a list, all of whose elements are of type integer. There is a int. There is a list, all the elements of which are of type integer. List char, but list char is the same as string. List of bools, list of strings, etc. And extending this logic, you can also have list of ints or list of integers. So here is a list. You see that the different lists that are elements of this bigger list can be of different lengths, but they all should be lists whose elements are of type int. You cannot have 1, 2, 3 and true false. This is not allowed. So 1, 2, 3, 1 is this list. Its type is represented as the base type with square brackets around it. True false true is of type list bool. Now in this, when we enumerated the list of all bools, we missed out one important case, which is the empty list. If you can have lists of 1 elements, lists of 2 elements, lists of 3 elements, etc., why can't you have lists with 0 elements? Okay. And but since you write lists with all the elements, you write a list as 2 square brackets, left square bracket and right square bracket, and all elements inside it. If there are no elements, you will just write a left square bracket followed by a right square bracket. But now what are the types of integers inside this? It could be any type whatsoever. So this is the important point. The left square bracket immediately followed by the right square bracket denotes the empty list for all types. So you can validly give this type list int or list char or list bool, etc. As we will see in a few lectures, in Haskell you will represent this fact that you can give any list type to this by saying that the empty list is of type list A, where A is any abstract type whatsoever. A stands for any type whatsoever. In other words, A is called a type variable. We will see this in a few lectures. Lists can be nested, as I mentioned before. So you can have the list consisting of the list 32, the empty list, and the list 777. This is of type list of int. Now lists are more like lists are unlike array, but lists are more like linked lists in other languages. If you recall, if you have experience programming in other languages like C or Java or whatever, you would have this kind of picture of a list. You have some reference pointing to the start of the list, and each list node, this is a list node, has a reference to the next node, and this stores the value. Each list node has two parts, one which stores the value and one which is a reference to the next node, and you will have a reference to the initial node, which you will typically call head, and your last node will have the null reference, which means that there is no next node. Okay, so this is the standard representation of lists that you have in other languages. Haskell lists are exactly like this, except that you don't need to worry about nodes having two parts and reference to next node, etc., etc. But internally, Haskell lists are singly linked lists like this. These are called singly linked lists. Internally, Haskell stores lists in some structure like this, but a programmer has much more flexibility in how you program with lists. Let us see what you can do with lists. Okay. So, internal representation is that you can always, so if you are given a thing like this in a language like Java or whatever, if you have a reference to a node, you can say node.value, or you can say node.next. Node.next takes you to the next value, or rather node.next points to the rest of the list. Node.value points to the current, returns the current value. So, that is the representation of lists in Haskell. You always view a list as first element followed by the rest of the list. Okay, in Haskell, a non-empty list we will see it in a minute. So, or rather, so we talked about how you can view a list, but you can also ask the question as to how you can build a list. So, you start with the empty list, you add an element to its left. That gives you a new list. You add an element to its left, that gives you another new list. You add an element to its left, that gives you another new list. You add an element to its left, that gives you a new list. So, you can think of every list as being built up like this. So, therefore, you can also decompose every list like this. Okay, this is the main idea. So, the operator to append an element to a list is append an element to the beginning of a list, prepend I should say. Is colon. Colon is the name of this operator. Remember this distinction, colon means construct a list, list constructor as we call it. Double colon is to say of type, right. So, when you want to say that an expression is of some type, you will put double colons. If you put a single colon, it means that you are trying to construct a list. Yeah. So, when you try to construct a list, the left argument of this colon has to be an element and the right argument has to be a list. Right argument is of type list A. Yeah, you will always try to prepend an element of type A to a list of type, to the beginning of a list of type list A. Yeah, so all Haskell lists are built this way, starting from the empty list. So, the list 1, 2, 3 within square brackets is actually one prepended to the list consisting of 2 prepended to the list consisting of 3 prepended to the empty list. Okay. And since Haskell has ways of reducing clutter in code, recall that long ago I mentioned that this in the last week's lecture I mentioned that something like this type is automatically interpreted as A intersection B intersection C intersection D, or in other words the arrow symbol is right associative. Similarly, colon is also right associative. Therefore, 1 colon 2 colon 3 colon empty list is interpreted as 1 followed by the list consisting of 2 followed by the list consisting of 3 followed by the empty list. Yeah, so this is what we have. And you can, of course, there is no need for you to build a list starting all the way from empty list. You can always take some existing list and add elements to its front. Right, so how do you decompose lists? So you are given a list L, how do you access its parts? Yeah, so if your list is empty, there are no parts. If list is non-empty, then it has to be some head followed by, typically it is called head and tail, it has to be some head which is an element followed by a tail which is a list. Right, if list is non-empty, then you have a first element and then you have the rest of the list, and there are two built-in functions. One function is called head and one function is called tail. Head returns the H part of the list, tail returns the T part of the list. So head of x colon xs returns x and tail of x colon xs returns xs, and this is a very useful Haskell convention. It is a very standard convention in Haskell. Whenever you want to write lists, you can of course give any variable name to the pattern h followed by t, etc. But typically you will name the first element as x and the second element as xs. Xs is the plural of x. Okay, so it is like saying 1 followed by 1s or 2 followed by 2s. This would be the list which consists of many 2s. Okay, so this is just Haskell convention. You can of course name, you can use any name. For instance, here I could have said h colon t, and then I said that head applied on h colon t returns head h, and tail applied on h colon t returns t. I could have said that, but x colon x is a standard convention, and it is better to learn it right up front. This is very important. Both head and tail are undefined for the empty list. So head and tail are what you may think of, what you may call unsafe functions. Unsafe functions because they will cause a runtime error. What is a runtime error? Errors can be roughly thought of as two: compile time and runtime. Compile time errors are those that will be caught by Haskell when you try to load it in GHCI, whereas runtime errors are those that will print an error message and abort in a bad manner when you actually try to run a particular expression with when you invoke a function with on some actual arguments. Okay, so that's runtime errors are bad because when you try to load a function, load a file with some various programs into GHCI, if it immediately compiles, you have to go back and fix the errors, and you can again recompile till it does not compile, does not complain anymore. But runtime errors are bad because there is no complaint from the compiler. You will face some bad behavior only when you actually try to run it. Okay, it is always better to catch errors at compile time, because you are catching it while you are programming rather than while you are running, while you are executing a program. Okay, okay. So note that head returns a value, tail returns a list. That's important. And here is another function null. Null is a function of type list A arrow bool. No matter what the list is, null applied on the list will check whether the list is empty or non-empty. If it is empty, it will say true. If it is non-empty, it will say false. Now let's look at how you can define functions on lists. Recall inductive definition of numeric functions. You typically say you define the base case for 0, and then for general n you will define f of n in terms of n and f of n minus 1, like factorial and so on. For lists, you have to do induction on the list structure. So this is important. It is called structural induction or structural recursion. Okay, so right. So the base case is now the empty list, and the induction case for a non-empty list of the form x colon x's, you define f of l in terms of x and f of x's. Yeah, because f is a function on list. Let's say f is a function on list int arrow bool, let us say, and f of empty list will be some expression. F of x colon x's will be some expression 2 that involves both x and f applied on x's. Okay, so this is the basic pattern of recursive definitions on lists. So here is a function. I want to add 1 to every element of a list. I have an integer list which is my input. I want to produce an integer list which is the output. I want to add 1 to every element. So now that we know about null, head and tail, here is what you could do. If null L, then empty list, because adding 1 to every element of an empty list will still produce an empty list because there are no elements. But if I do have, if my list is like 2, 3, 5, let us say, then I will take the head which is 2, I will add 1 to it which becomes 3, and then I will do add 1 to the tail of the list which is 3, 5. And once again this should produce 4 colon add 1 5. Add 1 of empty list is just empty list, so this should produce 3 colon 4 colon 6 colon empty list, which is nothing but the list 3, 4, 6. Okay, so this is the this is how the computation would evolve. Recall again that here computation doesn't mean that you have to, something is stored somewhere and you are changing it, rather it is just that you are trying to apply the definition and rewrite it. It's like if you have 2 plus 3 times 5 into 5 plus 6, you will first rewrite it as 2 plus 3 times 11, and then you will rewrite this as 2 plus 33, and then you will rewrite this as 35. That is exactly what is happening here, except that instead of arithmetic operators and built-in rules, somehow here these are not operators, but these are user defined functions, and instead of built-in rules you will apply the function definitions to get what you want. Okay, right. So this is a first example of a list program, but unfortunately what will happen is that Haskell will not compile, Haskell will complain. Unless you turn some special flags on, etc., by default, at least the latest versions of Haskell, will not compile this program. Why? Because head and tail are unsafe functions, as I mentioned. So it is possible for head to return to be applied on the empty list, therefore it's unsafe. It's possible for tail to be applied on the empty list, therefore it's unsafe. In this case, it is a safe use of head. You are applying head to L only after checking whether L is null, and you are applying it only in the case when L is not null. But Haskell doesn't do this extra analysis. Okay, as far as Haskell is concerned, it is just noticing that head is being used and it will immediately complain. Okay, so in GHCI you can try to run examples by applying head, etc. But when you add this in a program and try to load this into GHCI, it will complain. We will see this when we look at the demo session for this week. So what do you do then? Okay, here is what you do. Recall that we talked about let, etc. and I also said that let can be used as just a part of an expression. So you use this. So you say that if null L, then return, then the value is empty list, else you decipher L as x colon x's. Okay, by you say let x colon x's equals L. This is one nice thing about let as well as where. The left hand side need not just be a variable name, it could also be a pattern. You can say, recall we also said that let dm equal div mod n10 in something 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 in an earlier program. So you can use let and you can use a pattern on the left hand side. Here we are using here we use the pair pattern, a pair consisting of two elements, first element which I am calling D and second element which I am calling M. Here it's a list consisting of a head which I am calling X and a tail which I am calling X's. So you can actually do this let. For some reason Haskell allows this, it doesn't allow head, even though I could do x colon x's equals let x colon x's equal empty list and that would fail at runtime, but Haskell lets the pattern assignment fail, but it doesn't allow you to do head. Okay, so this is the variation that you have to use if you want the program to compile. You will say let x colon x's equal L in x plus 1 colon add 1 x's. Okay, so using these patterns to decompose the list actually makes it easier to write the right hand side. Instead of writing head of L plus 1 tail of L, etc., you can just write x plus 1 x's, right, directly. Okay, so that's so much about adding one to all elements in a list. I can consider another program which is to compute the length of a list. So once again I am saying my length because length is a built-in function. It's part of the standard library. So if you try to define length, it will complain saying that you are trying to redefine, or it will let you define, but when you try to invoke the length function on something, it will ask, please clarify which length you are referring to, your own length or the standard library length. Okay. To avoid all this, when we write small programs like this just to learn Haskell, we will sometimes reprogram some built-in functions, but we will call them using a different name, and the typical strategy is to use my and then just say whatever the function is, my length, my GCD, etc. By the way, here is another name that you might encounter instead of standard library, that is called Prelude. Prelude just means that it's the set of libraries that Haskell loads by default inside GHCI, or when you compile using GHC, these things are available automatically to you. Okay, so once again there is a problem because you are using tail of L and tail GHCI won't compile this program without complaining. So you have to use this. You say if null L, then the length is 0, else you let L be x colon x's, but you are not really going to use x. So just like long ago we saw in pattern matching definitions, you can use underscore to signify that I don't care what the I don't care to name this part at all. So you can say underscore followed by xs, because you don't care about the actual element, you just want to say 1 plus my length of xs. Okay. So if you want to talk about length, len, let me use len of 1, 2, 3, let's say equals, you will recall that this is nothing other than 1 colon 2 colon 3 colon 4 colon empty list, and this would simplify to 1 plus len of 2 colon 3 colon 4 colon empty list, which will simplify to len of 3 colon 4 colon empty list, which should simplify to 1 plus len of 4 colon empty list, which should simplify to 1 plus len of empty list. Len of empty list is 0, so this should simplify to 1 plus 1 plus 1 plus 1 plus 0, and that is nothing but 4. Okay. So this is how the computation will proceed. Okay. So now, rather than go through all these roundabout ways of defining functions on list, one can straight away use pattern matching. Okay.